Hello, so in the previous video we have looked at divergence, right? So in this topic we have divergence, and another part which is going to be what we discussed today will be on Gauss law. Gauss law actually came from this this word Gauss is actually derived from this German mathematician. His name is Carl Friedrich Gauss. And later on, probably when you learn electromagnetism, you would learn more about him and how he is actually one of the most prominent mathematician of all times, because he's also one of those who contributed a lot on to the Maxwell equations. So anyway, we will see how divergence will be related to Gauss's law. Okay, so what do we need to know about Gauss's law in this video? Gauss' law actually states that electric flux through any closed surface is actually equal to the total charge Q enclosed by the surface, alright, divided by epsilon naught. So do you remember epsilon naught? So basically epsilon is your dielectric constant or permittivity, alright? So the naught here basically means free space. So what it actually tells us here can be actually expressed in its mathematical term, in which it says that the electric flux, right? So I'm just going to put this in terms of E dot n cap ds, alright? So what it says here in this first part, where electric flux through any closed surface is equivalent to my total charge Q enclosed by the surface. Alright, I'm just going to put E enclosed here, or ENC, over epsilon naught. Alright, and if you're just wondering, okay, here you go again, you see electric flux. Now this is what Gauss law is about, so this will be the important formula that we need to remember. Alright, and how is it related to divergence theorem? I mean, remember earlier we looked at divergence theorem, isn't it? And how divergence theorem could be an easier way for us to get the total flux. So if I express my divergence theorem to get my total flux, then I'll have a divergence of E with respect to dV, therefore the triple integral. And if you recall, if I am having a total charge Q with its charge density, alright, charge density, let's call this rho V dV, volume charge density of rho V, and I replace this to my Q enclosed, replace Q enclosed with this, right, the numerator here. And if you compare side by side, then you will see that this part here and this part here is basically the same, isn't it? So if we take this out, then we can also show that my divergence of my E is actually equivalent to my rho over epsilon naught. Alright, or this, if you still remember, that's your partial derivative of your E. Alright, so that's actually all about Gauss theorem, but what it says here is that it becomes useful when it comes to you trying to find sometimes the total charge, or sometimes in the clue they will give you some charge, alright, and you're supposed to find the flux. So from the mathematical equation itself, you sort of will know when to use it, alright. So let's visit how this Gauss law is applied, as what you see in this rectangular box here, alright. So one of the most common part here, I'm going to show you two different kind of questions, alright. Let's start with the most simple one. And suppose that we have thin spherical shell, alright. Suppose we have thin spherical shell of, let's give this the radius r0. Okay, and what it has is that it contains uniform and continuous electric charge Q. Okay, and now they're asking you to find the electric field at first outside the spherical shell and inside the spherical shell. Alright, so if I am going to imagine this, I have thin spherical shell, alright, and I have uniform and continuous net charge, alright, and I have it at radius of r0. Alright, so assuming that, okay, I have my electric flux, it's moving this direction because why? At every surface and all that, remember my electric flux is supposed to be at normal of the surface, alright. So can you guess what field is this? So positive will always go to negative, right? For electric field. Let's assume it in as such, alright. So let's deal with it. Let's deal with us finding the electric field outside the thin spherical shell. So that's when, alright, what it is being mentioned earlier is that your total electric field will be equivalent to the Q enclosed, right, by the surface over epsilon naught. So usually when it comes to range like this, we will need to see first, the constraint here is to find it at the outside the spherical shell. Alright, so the first thing that we want to do is to choose the region with points outside the thin spherical shell. Alright, so if I just simply choose, I'm gonna just, as long as you circle it outside the thin spherical shell, it will do. Alright, so now we'll look back at what it mentioned from the formula. Formula gives us E dot n cap ds. Alright, and my n dot ds, n cap ds is also my the normal component, right? So E dot n cap ds here is basically represented by each of these arrow here. Alright, and because we're talking about, and usually for Gauss law, we usually talk about uniform and continuous charge. And when it's uniform and continuous charge, it basically means that my electric field is uniform, right? Then basically at every point, right, it is fair to say that it actually has the same or equal magnitude of my electric field, alright, because it's uniform. So no one field is actually greater than the other, so it's actually uniform, and therefore I can actually just take this out. And the best part of it is that, alright, on my ds area here, if you remember, basically it's the surface area, isn't it? If we're talking about spherical shell, and the surface area of my shell can then be represented as 4 pi r square. Why so? Because 4 pi r square is also the total surface area of a sphere. Alright, so that's one of the things that is interesting here. And what is it equivalent to earlier for the Gauss law? It's equivalent to Q enclosed over epsilon naught, right? So in this case, it will be equivalent to Q enclosed over epsilon naught. Alright, in this case, it's just Q as given. So therefore, my electric field will then be just my Q over epsilon naught and 4 pi r square. Alright, and one of the most important part also is to remember. Alright, so what do I have for my electric field? My electric field is a vector, and therefore you also need to put it in terms of the vector direction. So in this case, let's just take this as ER. Alright, just to indicate that it's actually of radial direction. Okay, so this is for outside a thin spherical shell. Okay, now what if it's inside? That's another part that we want to look at, right? So what happens basically means we have a thin spherical shell, but now what I have to choose is that I have to choose a region that is smaller than the spherical shell, which means my R naught is actually this side here, but my R will basically be smaller than my R naught. All right, so R here points to the purple circle dash circle that you see here. All right, so again I have E n cap ds, all right, equals to Q enclosed over epsilon naught. From the example earlier at the top, we can actually just indicate this as E 4 pi r square, isn't it? But then, here's the catch. Remember, from the start, it actually mentions that it's a shell. So what happens is that when it's a shell, thin spherical shell that has a uniform charge to it, it basically means that you only have this charge on the surface of the shell. Because why? Inside the thin spherical shell, it's actually hollow. So imagine like a ping pong ball, for example. So imagine that the charge is all on the side that you can touch, and whatever that's inside is actually hollow. So what does it mean when it's hollow? It means that there's no charge. And when there's no charge, what does it mean? Zero here. All right. Therefore, your electric field is actually zero for it to be inside the shell. All right. So now that you have seen this example of the range of inside and outside thin spherical shell, of course, things get actually more different when it comes to a sphere. All right. So for example, if you have a sphere, all right, and let's say now we just move on to the second example. Instead of shell now, you have a uniformly charged sphere with electric field inside, all right, and it's of radius r, let's say, all right, and then it also has charge density of rho. Okay, and what they ask you is to use Gauss's law to find the electric field, all right, for inside the sphere. So how is it different? Again, remember, the first thing we should do is to choose the region. So in this case, when we choose the region, we want to find it inside the sphere, isn't it? So what we do is that we just sort of like, again, with the purple pen here, I'm going to put this here, all right. So this will then be my, let's call this something else. If this is a small r, all right, small r for the radius of the sphere, so the radius of this small purple sphere, let's call this I don't know, let's call this A, all right, doesn't matter. So once we have chosen the point, okay, so we go by my E dot n cap ds equals to Q over epsilon naught, right? And then since they give you your charge density of rho, right, volume charge density of rho, basically, if you recall, this also means that I have this of my rho v dv over epsilon naught, right? So again, my electric field, since it's uniform, I can just write it as such. And again, I have 4 pi r square as the surface area, right? And then I have this, which is rho v dv over epsilon naught. Okay, and now the part is that if I wanna, and rho v will just basically be sort of like a constant, right? Because it doesn't affect anything to do at all with my integration of dv. So this is the part that we actually refer back to the definition of Gauss law. Gauss law states that, right? So what does Gauss law say? Gauss law states that your flux through any closed surface, which is the left hand side here, is equivalent to total charge Q enclosed by the surface. All right, we're talking about enclosed by the surface. What surface? That would be the surface of which in the region that we choose. All right, so in this case then, how we solve this dv will then be exactly the same. And since this is a sphere, all right, so the volume of my sphere, if you still recall, that would be 4 over 3 pi r cube, isn't it? So again now, this is the general formula for my volume of my sphere, but since we're talking about region or total charge that is enclosed by the surface, and we always refer to the surface that we actually determine in this purple circle here, and therefore we need to replace this r of which radius. This r will then be replaced with a, all right, because it's of radius a, because the Gaussian, so in other words, your Gaussian surface is denoted by the purple dash here for the surface, and therefore the surface enclosed is also given by the radius a. All right, so do you see the difference here? I mean, like when it is inside a spherical sphere, you actually get some charge and you get electric field for it. And therefore, if you want to get your electric field, basically, I'm just gonna put this left hand side to the other side. All right, then it becomes rho v of epsilon naught 4 over 3 pi a cube. All right, and then this will be 1 over 4 pi r cube. All right, and in this case, your r cube, okay, you can see that it can actually be sort of like being simplified. And of course, sorry, I have forgotten about this as well. We're talking about the region that's enclosed by the surface, right? So in this case, that will be of A as well. All right. So in this case, this will be A, and therefore this will be A. So you can see that we can actually simplify this, and then it becomes like a rho over epsilon naught. You still have the 3 there, and then you will leave you with an A. All right, and don't forget, I just indicate this as the vector in the radial direction. All right, so that's the difference here that you can see. But with Gauss law, it becomes easier for you to search for the answer. All right, so please give it a try. Okay.